This class is about ferromagnetism, and this is the from Wahhab's text section 16.12 and section 16.13. And in ferromagnetic materials, the relation between magnetization and the applied field H is non-linear. That is, as applied field increases, magnetization increases, but in a non-linear manner. To explain this kind of non-linear relation between M and H and the existence of a critical temperature, there is a critical temperature Tc in ferromagnetic substance, and below Tc the material will be a ferromagnet, and above Tc the material will be a paramagnetic material. That is the critical temperature of ferromagnetic material. Below the critical temperature, the material will be a ferromagnetic material, and it will be a paramagnetic material when the temperature is above critical temperature Tc. And both these things, that is the nonlinear relation between M and H and the existence of such a critical temperature, was explained by Weiss using the concept of domains, using domain theory. According to Weiss, ferromagnetic material consists of different domains, and this is one domain, this is another domain. And the peculiarity of domain is that within the domain the magnetic dipoles are oriented in a particular direction, and this is another domain, and the orientation of dipoles is similar, and this is another domain where the dipoles have a different orientation. And within a particular domain, these magnetic dipoles have similar orientation, and the total magnetization of material is the vector sum of magnetization due to each of the domains. And the existence of these domains in which the magnetic dipoles are similarly oriented or oriented in a particular direction was explained by Weiss using Weiss molecular or Weiss exchange field. It is known as Weiss molecular field or exchange field. And this theory is to explain the concept of domains in ferromagnetic material. And according to Weiss, in addition to the applied magnetic field H, there is another factor lambda m, and in total it is the exchange field. That is, there exists an internal molecular field, also known as the exchange field, acting on the dipole, and the internal molecular field is the total of the applied field and lambda m. That is, in addition to the applied field, there is another contribution, the contribution from lambda m, and that is the field which is applicable in the or experienced by the dipole, that is known as the exchange field. And lambda is known as Weiss constant, it is a constant known as Weiss constant, and m is the magnetization, lambda is Weiss constant, and this is the exchange field experienced by the magnetic dipole. And this exchange field also obeys Curie's law. What Curie's law states is that the ratio magnetization to the field, here it is the exchange field, that is equal to C by T, inversely proportional to temperature, and is equal to C by T. C is the Curie constant. C is the Curie constant and T is the absolute temperature. And remember, this exchange field also obeys this Curie's law. This law is known as Curie's law, that is m by h inversely proportional to temperature or is equal to C by T, where C is the Curie's constant. From this, we will be getting the value for critical temperature, that is m by h Ex is equal to C by T, and from this we can write this as using the exchange field. What is exchange field? Exchange field is a field experienced by the magnetic dipole, and that is equal to h by lambda m, that is m by, use this equation, h plus lambda m is equal to C by T. Again we know chi is equal to, the susceptibility chi is equal to m by h. Now we need the term m by h. For that, m is equal to multiply Ch plus lambda m divided by T, then divide by h throughout. M by h is equal to C by, dividing h by h, 1 plus C by T plus 1 plus lambda m by h, that is equal to C by T plus lambda C by T m by h. And take this m by h from left to or right to left, that is m by h into 1 minus lambda C by T is equal to C by T. The final equation is m by h into 1 minus lambda C by T is equal to C by T, is equal to C by T